All right, let's dive right in. Hi,
Sounds
everyone.
good.
Okay, great. Hi,
Sure.
everyone. My name's
All right, let's get
Megan.
it.
I,
Go for it.
I'm Marlboro's Alumni Engagement Manager, and I am so excited to welcome you to our March Aiming High event. I think you are really in for a treat this evening with our speakers. But before I officially turn it over to them, just a couple Zoom tips for the evening. We are definitely going to have some time towards the end to take some questions from all of you. So please don't be shy and drop those into the Q&A box, which should appear just at the bottom of your screen. It literally says Q&A, and you can open that and type a question in there. I will also be monitoring the chat throughout the event, just in case there's any logistical or technical issues, though probably our guests couldn't answer them a lot better than I can, but I'll be around to help as best I can. But again, for questions for our speakers, please put those in the Q&A box so we're sure to see them. And I think that's it for Zoom housekeeping. So I guess without further ado, it's my absolute pleasure to introduce two of my incredible colleagues from Marlboro, Dr. Darren Kestner and Mr. Andy Whitman. Dr. Kestner teaches math and computer science and serves as the STEM program co-head at Marlboro. In addition to developing the computer science curriculum at Marlboro, Darren works with the faculty in the math, science, and visual and performing arts departments to include computational thinking and coding in our existing classes. He also supervises students in their research and interdisciplinary projects involving computer science and engineering. In addition to having taught at Marlboro and other secondary and college levels, Darren has over 20 years of experience as a software developer in various fields, including computer security, computer graphics, and computational biology. He has published several scientific papers and open source software projects and regularly runs computer workshops for teachers and research scientists. Mr. Whitman is the STEM program co-head along with Darren. His primary responsibility is overseeing Marlboro's award-winning robotics program, which I know you'll hear a lot about tonight, which includes 4 teams competing in the first technical challenge. He also teaches 8th grade science and computer programming classes in the processing language. In all of his classes, he loves incorporating creativity, iterative design, and how computer science and fabrication technology can empower students to make almost anything. So like I said, incredible and accomplished colleagues that I feel really lucky to get to work with at Marlboro. And I am going to hand things over to them to introduce Marlise and get things going.
Thanks for the great introduction, Megan. Actually, I wanted to say that Andy and I feel like we're the lucky ones getting to work with all of the great students who go on to do amazing things like what Marlise is going to tell us about. So that's really why we're here, and we want to hear what Marlise has been doing. I wanted to say that Marlise finished Marlboro the year right before I started. So I never got to teach Marlise or to meet her in person. But she did work with Mr. Whitman. She was one of the captains of the Marlbots that year, her last year. And later on, following in her footsteps, my own daughter, Emma, who's in the audience, was the captain of the Marlbots in 2019. So anyway, I'll turn it over to Andy to say a few words before introducing Marlise.
Awesome. Yes. So you already know that Marlise was graduated Marlboro class of 13. And after Marlboro, she went on to receive her Bachelor of Science in Aeronautics and Astronautics from MIT in 2017. She then completed her master's in computer science in January 2020 at MIT with a focus on multi-agent coordination for exploration of dynamic environments such as the ocean. I'm looking forward to hearing more what that means, Marlise. She's currently a PhD student in computer science at MIT's Computer Science and Artificial Intelligence Laboratory. And she has also interned at a number of different companies throughout her career, including companies that do aerospace and self-driving cars. And I know that Marlise is very interested in applying her research in artificial intelligence and autonomous systems to really further our knowledge of the universe beyond Earth. So I know you've got a special interest in extraterrestrial things. But as Darren mentioned, I really know Marlise best as one of the founding members of the Marlbots and a former captain of the Marlbots. And, as Darren said, I just feel so grateful to work with students like Marlise because, you have really left a tremendous legacy here, and the institutional knowledge that the robotics teams have gained during the time that you were on the robotics teams has really helped lead to their success today. So I was really happy to learn last week, Marlise also gave up some of her time to talk with the robotics students on an alumni panel. And I learned that she's also mentoring a First Tech Challenge team. So that was really exciting to hear. So I'm super excited to be here and really honored to be able to talk with you today, Marlise. So I'm going to turn it over to you, and then we would welcome any questions from the audience throughout. You can drop them into the Q&A box at any time, and yeah, we'll see where this conversation goes. So over to you, Marlise.
Awesome. Let me just share the screen really quickly. All right, can you guys see these slides? Okay. Cool. Yeah, so I'm Marlise. I'm just going to talk a little bit about my background and how I got to where I am, and then kind of dive into some of the work that I've done and the work that I'm doing in my research at MIT. So a little bit about me. I grew up, of course, in Los Angeles, went to Marlboro. I lived in Pasadena, so really right around the corner from JPL, which I think is one of the things that really inspired me to want to pursue aerospace. I was also a huge sci-fi nerd when I was growing up. I love all things sci-fi, books, TV shows, just everything. I thought nothing was cooler than extraterrestrial exploration. So I, of course, went to Marlboro. I joined the Marlboro robotics team when I was a sophomore. This is a picture of us in the back of the 8th grade classroom where we used to be before the innovation room that you guys have now. And really, Marlboro robotics is the first time I had any sort of coding or programming experience. It was sort of my intro to programming and kind of what got me interested in programming. I was software captain when I was a senior. And so that really kind of carried with me as I went on, but I still was drawn to the aerospace world. So when I went to MIT, I majored in aerospace engineering. I was in the Aero-Astro program at MIT in undergrad. As I went through the program, I started to realize I really did not like aerodynamics. I was terrible at thermodynamics, materials, and like structures just did not click with me. And so I kept on kind of going back to my programming experience and really realizing that algorithms and computation was where I was really interested in, but I wanted to kind of combine the two things. So after I graduated undergrad, I wanted to learn more about computer science and more about AI. So I stayed at MIT, and I'm still at MIT. It's a hard place to leave. And now I'm in the model-based embedded and robotic systems group. As a fourth-year PhD student studying computer science with a concentration in autonomous systems. So there's just been a theme in my life of like robotics and space all throughout. So on that note, I want to talk about autonomy in space. So hopefully you guys know at least the picture on the left. This is Mars Curiosity. That's been on Mars for about 8 or 9 years now. And the one on the right is Perseverance that just landed on Mars a few weeks ago, which hopefully everyone got to see. Really exciting. So these are both amazing feats of engineering. However, their onboard autonomy is pretty limited. So Perseverance has a little bit more onboard autonomy than Curiosity has. It's able to sort of plan its own motions and do sort of its own monitoring and repair. But still a lot of the decisions are being made by humans on the ground, sending commands up to the Mars rovers. And this sort of works for Mars. The 7-minute delay is really, it's only 7 minutes to communicate between Earth and Mars. And we know a lot about the Martian terrain. And so it's pretty good to do that kind of human in the loop decision-making when we're talking about the Mars rovers. However, as we start to think about pushing farther and farther out into our solar system, like some of the upcoming missions to Europa, for example, which is a moon of Jupiter, then we start to realize that it's going to be hard to communicate with any sort of system that's that far out. The communication delay is too long, and we also know a lot less about things that are that far out. So systems will have to be adaptive. And so that's kind of the thing that I'm interested in, is how can we make autonomous systems that are robust and capable of reasoning in complex and dynamic environments and adapting to changes on the fly. So obviously it's really hard to do space research on Earth, but there's a lot of sort of analog environments and analog domains where we can kind of get the same sort of challenges that we face in space exploration, but on Earth. So a big one that we do in my lab is autonomy in the ocean. So autonomy for ocean exploration. The ocean is a great analog for space exploration because it's sort of the most unexplored place on Earth. So we know kind of equally little about our oceans as we do kind of about our solar system. Deep oceans are hard for humans to get to if you think about the capabilities and limitations of a human diver or human dive team. But robots have a lot more capabilities and can stay underwater for a lot longer. So we kind of can use them as a tool for exploring our oceans. However, exploring the oceans is still challenging. It's really hard to communicate with any autonomous vehicles that are under the water. It's a hazardous environment. There are kind of poorly mapped ocean floors. There are currents which change throughout the day. And so there's still a lot of kind of smarts that need to be imbued on these systems to make them robust in these types of environments when they're doing science, when they're exploring. These are just some examples of some like ocean explorers that we've worked with in the past. So how typical science operations for autonomous ocean exploration go. We have some scientists. They kind of determine what they want the autonomous systems to be doing. Maybe it's monitoring coral or kind of sampling temperature fields under the ocean. They will write a script, sort of detailed instructions for what each agent should do, step by step, kind of put that on the vehicle, deploy the vehicle into the ocean. Once it's underwater, we can't really communicate with it. So sort of on its own, doing its own thing, following the instructions step by step. And if there's any issues, it kind of just pops to the surface and says, hey, I came up with an issue. And then we collect the vehicles again. The scientists go through, analyze the data, analyze the health of the vehicles that were under the water, and kind of do this whole process again. So this works perfectly fine for like a single autonomous agent. But if we want to start scaling up these operations to multiple different agents that have different types of sensors, that have different battery capacities and all these different types of things, then it kind of becomes a big cognitive burden on the people who are managing the ship. And the people who are on the ship are people too. They've got to sleep, they've got to eat. And so what my team, my lab mates and I were interested in is how we could develop an autonomous system that could help the scientists aboard the ship with their decision-making processes, both on board the autonomous vehicles and on the ship, to kind of manage all the resources. So how do we go about thinking how to design a system that to do this? One question we like to ask is, what makes humans good at exploring new and challenging environments? Humans have been exploring new environments for hundreds of years. We explore new environments almost every single day. And so why are we good at it? There are a few key things I want to draw out here. First, we are adaptive and predictive. We can adapt to changes in our environment very quickly, and we can predict kind of how the environment is going to change around us very well. We are goal-directed. What I mean by this is we can kind of execute a very complex task given a very simple set of instructions. So if you were telling your friend that you need them to pick up something from the grocery store, you don't tell them to like take 5 steps out of their house, turn right, walk 10 blocks, turn right again, get to the grocery store, go to aisles 3, 4, and 7, then check out, then come back. You just say, hey, go to the grocery store and pick up these items and be back in an hour. And so that's the kind of high level language we want to be communicating to our autonomous systems with. We don't want to have to tell them step by step what they have to do. We just want to give them a high level directive and they can go and figure out how to do that. So to do that, they have to schedule and plan, which is something we do all the time. We schedule our day, we schedule walks, we schedule all sorts of things. We want to be able to have autonomous systems that do that. Another thing about humans that's really great is we're self-preserving. We care about our own safety generally. And we're good at sort of like diagnosing when something is wrong, when, when something doesn't happen right away or happen how we expect, we can kind of diagnose and figure out the issue and fix it and repair. So we want our autonomous systems to be the same. And finally, we're really good at coordinating and cooperating with others. We can communicate with other people, we can we can know other people's intentions and how their intentions impact our goals and intentions. And so these are all the things we want to try to imbue an autonomous system with. So kind of the system that my lab is working on is called Enterprise, in a very nerdy homage to the Star Trek universe. Basically, it's a system composed of several different decision-making components, each kind of with their own role. And they kind of all come together to form what we like to think is a bigger than the sum of its parts kind of autonomous system that's capable of handling a situation like a multi-agent underwater exploration mission. So to start at the top, we have Uhura, our communications officer. This decision-making component and the algorithms underlying Uhura kind of work with the user, so a scientist perhaps, take in what the user kind of wants to specify for their goals, for the science they want to collect, and negotiates with the user in case those goals are unreasonable or infeasible for some way, or kind of there's a conflict with, you're using this resource, but it's needed at the same time by something else. So that's what Uhura is doing. It's negotiating with the user. The next component we have is Kirk. Kirk is the captain of the ship, kind of coordinates all the high level activities. So the schedule for all of the agents, kind of allocating different tasks to different autonomous agents and kind of coordinating everything as a whole. Spock is our science officer. The algorithms underlying Spock basically take prior information about the state of the world or the state of information that you're trying to learn about and decides which kind of areas are best to go to that will further your knowledge of the particular scientific phenomenon that you're interested in. So it's going to basically choose which scientific sites to go to based on its prior knowledge, which is derived from typically knowledge of scientists. Then we have Scotty, our engineer. Scotty's responsible for coordinating, multi-agent coordination of multiple different agents, vehicles maybe that we were deploying underwater, making sure they don't collide with each other, making sure that their trajectories and paths are coordinated. For example, the research vessel has to go and pick up various underwater agents at different times. And so Scotty coordinates all that. And then finally, we have Sulu, our pilot, who is, which is doing lower level motion planning. So really going from point A to point B, all the controls needed to kind of direct each agent to get from point A to point B in a risk-bounded fashion, meaning that it's taking into account that the world is uncertain and we need to factor in those uncertainties when we're making a plan so that we're kind of prepared for any situation. And so all of these components work together to kind of give a robust realization of whatever kind of science mission that the scientists want to perform. So a real world example of this is our most recent underwater exploration mission was to Santorini, Greece in November of 2019. We were exploring an underwater volcano called the Colombo volcano just off the coast. And we were interested in this location because it's a relatively unexplored area. And we thought that it could harbor evidence of life that survives in extreme environments, which is something that's interesting as we also think about life in extreme environments off of Earth. So it was kind of an analog to a potential underwater space mission. We were controlling 3 different types of vehicles. We had a research vessel, which deployed all of the agents off the research vessel. We had these gliders, which are very sort of like agile, torpedo-like agents that kind of survey large areas. And then we had a manipulator, an underwater manipulator that could actually go down and take samples. And so kind of the goal of the mission was to have the gliders do a survey of the underwater volcano, decide what the best sites were to send the manipulator down, to actually collect samples and make sure that all the agents were being coordinated with each other, not getting in each other's way, being safe, etc. So I think the biggest thing that I learned on this expedition was that all good science has obstacles and like things that unexpectedly go wrong. So when we got there was a big delay and everything because the batteries for the gliders were stuck in Germany. And we almost lost our manipulator on a previous mission because it almost got trapped under the ice. And my favorite anecdote is that one of the gliders surfaced a little farther away than we were expecting. And a fisherman actually came up to the glider and kidnapped it onto his boat, claimed it was his and held it for ransom. And we had to send one of our Greek scientist over, and she gave him a very stern talking to and reclaimed our glider. So you never know what's going to happen in the field. We also have very nice working conditions in these tiny little rooms on board this cable laying research vessel. All that being said, we did do good science. This is an image of kind of the close-up of what some of the underwater terrain looks like. This white line is the path that we autonomously planned for one of the gliders to go to. And right here is where we actually found a previously undiscovered hydrocarbon seep, which is really cool. It got coined Spock's candle. And if anyone's interested in reading more about this whole expedition, let me know. I can point you to some articles that were written about it. So this is just like one of many underwater exploration missions that we did, and we have some more upcoming, including one to the Arctic, where we're going to be going kind of under the ocean, under the ice, to do kind of under ice shelf monitoring. So those are ocean projects that I've done in the past. Things that I'm working on now, just to give you an idea of like how varied sort of this field is, and there's a lot of different domains. One project I'm working on, we're trying to develop a system that's able to kind of, while it's executing in the world, learn about the world and factor that in to its own goals and its own kind of mission that it's doing. An example that I like to give is, if you imagine you're walking and you sprain your ankle, you don't just or you twist your ankle, you don't just like fall down on the ground and like lay there and like give up, because that's it. You get up, you sort of test out how much weight you can put on your ankle, and then you kind of develop a new model of how to walk, which is limping, using the knowledge that you just learned. And so we kind of want to imbue an autonomous system with the same idea. If something goes wrong, or if it doesn't have a complete understanding of the world, can do a little bit of exploration, gather some data, create new models, and use those models to kind of continue on carrying on its task. We're going to be using this sort of very old 1993 video game called The Incredible Machine, in which players sort of use these components to build a contraption that achieves some goal. And as a human, you kind of use your common sense knowledge about these components to play the game. You explore to kind of get more precise models of each of the components, and then you can kind of solve the puzzle. And so we want an autonomous system to be able to do the same thing. Another project that I'm working on has to do with space, which is exciting for me. In this case, we're doing a kind of mission concept for asteroid flyby that would be using onboard autonomy to do its science. So we're particularly interested in measuring ice content on the asteroid 24 Themis. And the challenge is that our observation systems on Earth, ground-based observing systems, don't have high enough resolution to tell us which craters we want to image before we get there. And so we really need, this is a great case for onboard autonomy, because we need to be able to, when we arrive at the asteroid, send some scouts to the asteroid, be able to have those scouts take some initial data and send it back to some like larger mothercraft. And then the mothercraft has to decide based on that data which craters are going to be the best to image. And with a flyby, you really only have like 1 hour when you're kind of above this asteroid. And so it's not enough time to wait for Earth to tell you what to do, to wait for people in mission control to tell you what to do. The spacecraft really has to make these types of decisions based on science and information, make decisions about what it needs to do to get the best data. So those are just a couple of the projects I'm working on now. That was kind of a fire hose. So let me know if you have any questions. But that's just an overview of some of the things that I think about and that I work on in my lab at MIT.
Wow, thank you so much, Marlise. I'm a little blown away, but you explained everything so well that it actually makes a lot of sense. And I'm glad to see that the pros are still giving their robots and machines kind of nerdy names, because I know.
Of course, we have to have fun.
So I think, I guess one question that Darren and I had was, AI and artificial intelligence is a term that's used a lot in a lot of different contexts. And, we're all a little bit aware that we have some AI in our phones, and then Alexa and Nest and things like that. From your perspective and the work you're doing in the exploration, what are the capabilities of artificial intelligence, and what are the limitations? What can it do and what can't it do?
That's a great question. So
Actually, maybe just let me add one thing is,
yeah.
and this is coming from a perspective of, we see on, what we see in real life is things like Netflix recommendations and autonomous cars, like that sort of thing. And of course, in sci-fi, we see stuff like Data, or anything on Star Wars or Star Trek. Really, we have all these. So where is reality? Where's the line between reality and science fiction?
Yeah. So I think one. How I want to start answering this question. It's a big question. So I guess AI in general, or how I might define it, is sort of any sort of computer that is doing reasoning about a task, taking something as an input, doing some transformation, and then returning something as an output that is different from the input and that is maybe non-obvious from the input. Or you have to do some reasoning to get to the output. There are many different types of artificial intelligence. I know machine learning is a big buzzword. Machine learning is not all artificial intelligence is. I would say that the research that I'm doing, the stuff that I explained in my slides, none of that had to do with machine learning. All of that was sort of like model-based, I would say, kind of non-learning, non-data driven methods for making decisions, like search algorithms and things like that. Where is the line? I think there are, in my mind, there's kind of two major camps. There's the data-driven approaches and the model-based approaches to artificial intelligence. The model-based approaches are sort of what my lab is focused on. I think this means more that you, as a programmer, develop some algorithms, and those algorithms work because they have a model of how the world works. You kind of give your autonomous system kind of some understanding of how the world works. And then it uses that model of how the world works to make decisions. The data-driven approaches instead are saying, okay, we don't know how the world works. We're going to use a bunch of data, figure out how the world works, and then make decisions based on that. And so I think a limitation of the model-based approaches is that you have to give your system a model, and that model could be flawed. It could be oversimplified. It's definitely going to be narrow and limited in scope, because there's only so much you can write down, you can capture. And then the data-driven approaches are limited because you need data. And so if you are in a situation where you don't have a lot of data, or your data is very kind of specific or geared towards one particular task, then your artificial intelligence system could fail on certain cases. So like you mentioned Netflix recommender systems, that's like a very common kind of AI that is pretty easy to grasp in that, like, Netflix uses data from all of its users to basically train a neural network to predict what another user that it didn't have any data about is going to like. And so in that very real sense, Netflix is using all your data to like make recommendations to others, to make recommendations to you. And it kind of builds up this whole database of like what people like, and uses that database to make recommendations to other people. Yeah, wow. There's a lot to talk about there. I think that we're very far away from an artificial intelligence that can kind of like do everything, like really the human brain. I mean, the human brain has like billions and billions of trillions of synapses, and the largest neural network maybe has on the order of millions. So we're far away from like really replicating the human brain or something like that. And I would say like most AI systems are really programmed and developed for one particular task or some subset of a particular task. That's not to say that they aren't very capable at those particular tasks, but there's very different algorithms and different processes for different things. Yeah. Does that answer your question? I can dive deep into any more, or
no, of course, I know. We can see it's a big world. And as you were talking about that, I was thinking that probably even in your own work, you're seeing a combination of both the data-driven and the model-driven approaches. Because for something like an autonomous robot like that, you need a model-driven approach, but maybe there's something like image recognition that's on board that's got to be trained as by data. So there's probably going to be a lot of blurry lines moving forward, I'm sure.
Exactly. And I think kind of the next area of research, like one of the projects I mentioned at the end, is really trying to combine those two, trying to investigate kind of how you can leverage the power of both, because model-based approaches work really great in environments where you really don't have a lot of data, like when you're exploring under the ocean. But then model data-driven approaches work really well when you don't know anything about the environment, but can explore the environment and learn. Yeah.
So I had a couple of technical questions just about some of your research. So one of them was on that trip to Greece and when the thing was down in the crater. So you said that it found a thermal vent, but did you bring back samples from there also?
Yeah, we did.
And were they geological samples, or were there also biological samples?
So I don't think they were biological samples. I think they were samples of just like the water column. So kind of goes down and gets these like tubes of water. And I think like some geological samples. The scientists that were on board with us were primarily like geologists and volcanologists. So they were interested in the rocks and things.
Right. I'm interested because I've worked with biologists before, so there's a lot of interesting biological questions. Of course, that's why you'd be visiting thermal vents, right, to search for extremophiles or something like that. That's the same idea as when you're searching for life on another planet, which is
exactly
super exciting.
Exactly.
So, yeah, very cool stuff. We had a question from someone in the audience. How much has math and coding taken place at your work at MIT? So this is from one of our students who's an up and coming math encoder who's interested.
Yes, it is. I'm and maybe as my own addition to that question, what sort of skill set do you have and bring to this work? What sort of skill set do you need to do the work that you're doing?
Yeah, so programming is something that I do. Computer scientist, I program code a lot. I think I would advise anybody interested in STEM at all to learn some programming. Even if you don't want to be a computer scientist, you probably will have to do some coding in your work. There was a question about math. Yes, I use my math skills all the time. Still use calculus. Still use my differential equations from early on my college career. So it's important. It stays with you. More than anything, though, I think my engineering background in aerospace, sort of this like the ability to like solve problems and just like the sort of whole process you go through of like identifying the problem, figuring out how to solve the problem, doing research into the problem. Most of research is really kind of having discussions with people, reading, just like thinking about what problems there even are to solve, and like how you could break it up into smaller chunks to try to start solving them. And then once you go through all of that, do you actually start coding and experimenting with that.
Excellent. You know, I see, I don't know, Darren, if you saw Katie's question that just popped up, but I thought that might be a nice segue into one that you had for Marlies.
Sure, but I see a couple above that, so maybe we could do one of those from above. I see this, maybe this is a quick one. I don't know if there's a quick one first, but what's the most interesting or fun project you've worked on?
I think the Santorini ocean project was pretty fun. I also got to go to Hawaii a few years before that, and I actually liked the Hawaii one more. It was less of like a science mission with a science objective and more just like a bunch of scientists coming together. We were kind of coming there as the kind of computer scientists who wanted to put our autonomy on board these vehicles, but then there was all these other kind of universities and institutions coming with their different robots and just kind of like throwing them in the water, trying to figure out how they could cooperate together. And it was just like a really fun experience of getting to work with people who are slightly outside my field, but still very relevant. So the melding of minds was really cool.
Yeah, no, that's great. Then that reminds me of two things that I wanted to point out to our students who are in the audience. Is one is that there's a lot of travel opportunity in science, and two is that in computer science, you're valuable to a lot of different people, a lot of different groups. And so you can get invited to do a lot of different cool things. So, but yeah, Mr. Whitman, you're right. This question from Katie would be great, kind of as a segue into thinking about, as a school, we've been thinking about ethical implications of artificial intelligence. And I know we're going to be thinking about this over the next year, definitely. So the question from Katie is, what ethical questions have come up in your research or education in AI and robotics?
Yeah, so this is a good question, another big question. So something that I'm thinking about, I mentioned to Darren this before, this is sort of separate from my current research, but I'm working on a startup that is doing kind of an AI-powered solution for custom wigs and hair extensions for Black women specifically. And through this process, it's kind of, we have really realized as we're trying to develop our algorithms that representation in data is really lacking, as kind of more and more AI-powered solutions are coming out for people to use all the time. There is sort of biases introduced when your data set is lacking representation. In our case, when we're looking for data sets of people's faces, people's hair, it's really lacking representation of people of color, of women of color, of people of color's hair types and textures. And so, I mean, that's just in the fashion and beauty space, but you can think about how that has ramifications for law enforcement, how that has ramifications for, I don't know, airport security. Like you could, the list goes on and on a lot of times in like the security space, right? When we're talking about facial recognition or anything that's using facial data, if that data set isn't representative, it can lead to a lot of problems. So that's just one ethical question that has come up in my work. Kind of another just general question, a general ethical question is obviously, especially like a lot of things I do could be used for a lot of different things. In the energy space, in the defense industry. And so kind of we like to think that we kind of use our research for the power of good. I'm really interested in robotics for science specifically, but there are a lot of people who do research, in fields that might not be as wholesome. And I don't know if it's necessarily like there are ethical questions that come up there, but it is sort of like the advancement of technology. And I think like as a society, these things are going to happen, and people oftentimes the failure of scientists is to just say, wow, this is so cool, can we do it? Not, wow, this is so cool, should we do it? So scientists will keep developing and keep putting these things out there. And as a society, I think we need to start thinking about, okay, how do we start to regulate these things? Like, what are the actual ramifications on like everyday life that this poses? And so I think it's less about like hindering the technology and more about building infrastructure around the technology to make sure it's being used for the right thing.
So maybe to follow up on that, you may have been following the news about Google and the ethics group in AI at Google, where they've recently fired a couple of their ethics researchers. I was wondering if you had any thoughts about that.
I haven't actually read that article, but I definitely have a lot of friends and people I know who are very very concerned with sort of how our everyday data is being used and kind of just collected. I don't know if you guys watch The Social Dilemma, but that's sort of like, along those lines, and kind of knowing and understanding. I mean, I don't think it's all harmful. I think it's just there's a lack of understanding from the individual consumer about really what your data is being used for, how broadly it's being used, how it's really never gone, no matter how many delete data buttons you click. And so I think like it's unfortunate to hear that Google maybe is putting less of a priority on that. And I think I'm hoping that there's just more, like more and more people are becoming more and more aware of how pervasive kind of the use of your data is in your everyday life, and like getting curious about really how your data is being used and by whom and for what. And it's really kind of at this point, it's more on individuals, unfortunately, to like start having a better understanding of that.
Well, maybe that is unfortunate. So maybe a more general question would be, do you think companies like Google should have an ethics group to kind of watch themselves? And is that enough? Maybe should we have better watchdog groups in government who are paying attention to that thing? Because it seems like a lot to put on, a lot of burden to put on a citizen to be checking on your privacy all the time, especially if it's all of us who are checking on our privacy all the time. So what do you think is a good, what are your thoughts on solutions for that?
Yeah, I absolutely think that, the biggest place where we're behind is in policy making. There's just, an example that I always go to is like for self-driving cars. Like self-driving cars are gonna come very soon. I don't know how soon, very soon. And there's just a whole host of issues, ethical and non-ethical. Just, how does car insurance work when you own a self-driving car? Like there's all sorts of like real issues that are going to start to arise, and we're so far behind in terms of all policy making to regulating how that's going to work. And I do think that it should be on the burden of the government to start to better kind of keep track and regulate these things. But I also think it should be on the burden of developers and companies to start educating people about kind of what they're doing behind the scenes. And I know that like especially more recently, there's been a bigger push for that. Yeah.
That's it. That's excellent. Darren, did you want to ask a follow-up about that?
Oh yeah, there's just one came into chat just now. How can it was a thank you for this talk from Catherine K. It looks like. Hello. How can budding moral philosophers and policymakers get involved with this effort? What are some organizations that young women in Los Angeles and the US can get involved in these areas?
That's a great question. I personally have not been super involved in policy making, so I don't have a great answer to that question. One thing that comes off the top of my head is MIT has a science policy initiative, SPI, and they do a lot of cool things. They have a lot of great talks, like great kind of reading recommendations and stuff like that for science and policy and the integration of them.
Yeah, I will say that there is another good organization called the Union of Concerned Scientists that's been really big on advocating for policy based on science in our country. And they probably have an AI section or something, like some kind of project devoted to that. I haven't actually looked, but as an organization, they work on a lot of different policy issues involving science.
On the topic of AI in high school, what sort of projects or what sort of things could students look at to get involved and practice with artificial intelligence in high school?
Oh, awesome. Yeah, there are some really great like online courses and like summer programs for like specifically AI. I think one of them is called Camp AI or AI Camp or something like along those lines. That's really good. And then I would say like there's just tons of online classes that universities post about all different things. edX is just a great resource. I continue to use edX to this day, which has classes from tons of universities and all things machine learning, you know, autonomy, kind of all those types of things.
That's awesome. I don't want to steer too much away from the policy, but I'm seeing a question here from Elizabeth in the chat. I'd love to hear more about, and that's about the testing process that you have to go through to get these autonomous systems to work. So she says, what does the testing process look like for these systems or algorithms ahead of launching them into ocean and space? Because I imagine it's hard to test some of this stuff on Earth. So how do you do that?
Yeah, so for the stuff we deploy, like in the oceans, for example, we have a lot of simulation capabilities, and developing simulators that are accurate enough is like a whole research area in and of itself. But we try to kind of simulate as best we can. We have simulators at very different fidelities. You can kind of first pass do it sort of text-based, what the mission looks like. Then we have simulators that are actually simulating the vehicle. We have outside of the computer, we have sort of hardware simulators. What literally is a box that sits on your desk that sort of is all of the brains and internals of the agent that you're going to be working on, but it doesn't actually move or go anywhere. So that's like the next step, just to make sure that like all the hardware is integrated with our software. And then we're lucky enough to live very close to the ocean and close to the Woods Hole Oceanographic Institute. They have these robots that we use to do underwater exploration. So we go down there, we throw stuff in the water there, test things out and see how it works. And then we do actually a lot of testing and integration when we're actually like there on board the ship, like where we're actually supposed to be doing science. It's a very iterative process. When it comes to like deploying things into space, it's a whole other different story. It has to work the first time, no matter what. There's no going back, there's no trying again. So they go through like very rigorous, the same sort of levels probably that I talked about, but over a longer period of time. And they try to recreate whatever environment that they're going to as closely as possible to try to work out those issues.
That's awesome. And I guess on a related note, I see Kimberly's question: when something does go wrong, how do you find out if something has broken something vital? And what does the autonomous vehicle do in that instance?
So ideally, the autonomous system would be able to a certain extent, repair itself when something goes wrong, kind of correct for it, depending on how badly something goes wrong. In a very practical sense, when we were on our ocean exploration missions, for example, when something goes wrong, we would sort of just signal the agent to abort and come to the surface where we could communicate with it. We could figure out what was going on, and we could send it a new plan if it needed a new plan to figure out what was going on. There has been cases when like our agents just sort of, our underwater vehicle like went rogue and just like took off in one direction and we had to go chase it down. That only happened once though. Yeah, so we hope that our autonomy is able to have the agent keep itself alive and keep itself going. Actually, one project that my advisor worked on a while ago in the 90s was Deep Space One, which was a space probe that went really far out to the outer edges of the solar system, and it was doing its own sort of diagnosis and repair of its systems on board on its own. And there's a lot of kind of deductive reasoning that goes into that. When something breaks, you have to kind of track down the root cause and track down why it's broken and then kind of go about fixing the issue.
Thank you for that, Marlies. I'm thinking about, there's some of the AI or some of the robots that I've seen coming out in the mainstream news recently, like Boston Dynamics Spot robot, or I don't know if you've seen Embodied Moxie robot, the one that talks to kids.
Yeah.
and so, as a parent, I'm thinking, oh, wow, how ubiquitous are these robots going to become? I'm wondering if there are areas on Earth that you see, AI equipped robots becoming mainstream and disrupting, our day-to-day lives in a big way.
That's a great question. I think for actual physical robots that move around, there are a lot of sort of like safety, like in someone's household, there's a lot of like, a household is a very uncertain environment. It's very hard to predict where things are going to be, where things are going to lie on a shelf. So that's why you see robots in sort of more ubiquitously in like manufacturing environments or things that are like more regularly controlled. I mean, we already have AIs in our households, Google Home, Alexa, all those good kind of voice assistants. And we have other types of robots like, Roombas and stuff that kind of are operating around us. I think the robots that are going to be more ubiquitous in our daily life are going to be autonomous cars. That's a huge industry that's kind of budding. And it doesn't seem like they're robots, but they are. They have onboard autonomy and they operate on their own. And that's going to start to just become part of our daily lives. I think another good one that you brought up is sort of like these AI kind of for kids and for education and like kind of companions. I've seen kind of becoming more and more popular. And it's very interesting how it kind of gives robots kind of a personality, but also like you empathize with them, which is a little bit odd. So yeah, it's hard to say like what will be the next big thing. I think from my personal experience, and I typically work with larger things, that self-driving cars are going to be the next big thing.
So, Mr. Whitman, I see a big question came in about more of a philosophical question. It might be a bit much to read the whole thing, but the gist of it is a quote from The Social Dilemma that says that algorithms are opinions in code and cannot think. But there's been a lot of research and a lot of money being poured into research into AI that can actually think rationally or can make decisions, more like a human. So, to what extent do you think it's possible for artificial intelligence to think rationally? Or do you think they're throwing their money away?
I mean, it depends on what you mean by thinking rationally. I think that there's a big, like you said, there's a big area of research in trying to sort of imbue, or this is sort of something I'm a little bit interested in, is like imbuing autonomous system with the notion of common sense, and sort of like how we're very able to quickly qualitatively deduce things using our common sense. And I think that there is truth in the statement that like algorithms don't really think, and most algorithms are very deterministic in that, given a certain set of inputs, what's going to happen, or at least the space of possibilities of what's going to happen, which is kind of hardly thinking, but thinking rationally, I don't know. I think it comes down to how you define rational thinking.
Yeah, I guess there's more. As I'm reading, there is actually more to this question. So there was she prefaces, "Thank you, Catherine Kuhn, for the very in-depth question here." So it's she's reaching back to some philosophies. So in particular, the idea that rationality is the ability to reason or critique and to make sense of your experience. So in what sense can do you think this is very speculative now, of course. Where do you think we can actually go with this AI in terms of kind of higher level thinking that's not just predicting things?
I think we're pretty far away from that. I think that's like you're right, like a whole kind of level of abstraction beyond like what most people are doing now. And obviously there are researchers who are very interested in like very cognitive level, like how can we develop very cognitive reasoning systems that are kind of more modeled off how humans think and feel about things. But I still think that we're pretty far away from having something like that realized. It's an interesting thing to consider. I don't know.
Yeah, I was thinking that too, as you were saying that you saw the glider was going away from you, and you didn't have any control over it. I mean, that's the problem with autonomous systems, right? Is that they can just get away from you and not come back. So that's not something you'd want your Roomba to do, of course.
Exactly.
Or the car that's driving you around.
Exactly.
I see a couple related questions from some of our students that might be a good way to start winding our Q&A down. And they're about, how you figured out that engineering and computer science was something that was interested to you. And I guess what inspired you to major in engineering? And I know since you sort of pivoted partway through to computer science, maybe what led you to that?
Yeah, so I feel like I've always liked the notion of like creating something, or like creating something that can do something cool. I think, and then for science in particular, a huge sci-fi person. I think that's really what got me interested in it, is I always wished that I could live in those worlds with advanced technology, and I just wanted to be there. And I think, but then specifically engineering, I realized I really liked the kind of the thought process and the problem solving skills that really goes into engineering. That it is, there's that kind of saying, I don't know if you've heard this saying, engineers are lazy. Like it's really just about kind of solving problems that make our lives challenging, and kind of wanting a world that is easier for us in general, and kind of finding solutions to challenging problems. And so I like that aspect. Why I switched to computer science, just sort of I realized as I was going through my aerospace degree that what I enjoyed doing most was, in addition to the kind of like the problem solving aspect of engineering, was coding and algorithms and computational thinking. And I just wanted to learn more about that and kind of get more of a background in that. And so that's kind of why I pivoted. And I also just kind of like being a little bit diverse in like what I'm thinking about. So yeah, that's why I switched.
So, computer scientists will tell you the same thing, that computer scientists are lazy. That's why coders automate everything, right? You can
Exactly.
you don't do anything manually. You automate everything, and you can do that if you know how to code.
Exactly.
Yeah, I was thinking you're going to have a very desirable skill set, Marlies, too. You've had experience with the hardware and the software and making it all work.
Mm-hmm.
I guess, Megan, are we getting close to winding this down? Because
Yeah, yes, I wish we weren't. I could listen to you all keep
Uh,
talking about all of this for a long time.
can I ask Marlies one last question and then we close it out? So I think you talked a little bit about this at the alumni panel that we had for the robotics students, but I'm just curious for you to tell us what's next for you, sort of, what does the conclusion of your PhD look like at MIT, and then where do you hope to go next from there?
Great question. I'm a fourth year PhD student. PhDs are long. So I probably have about 2 more years left. And then I'm a little undecided. I definitely want to go into industry. I'm not really sure which industry yet. I think I eventually want to end up back in aerospace. I've always wanted to work for JPL, and I hope to end up back there one day, or some other space related company. Right after I graduate, I'm not sure. There's so many kind of industries that could really benefit from the things that we research. Something that I've been interested in is sort of like the construction industry, and how a lot of kind of the multi-agent, like autonomous explorers could really, or a lot of those same ideas could really carry over to the construction space. So I don't know. See.
Well, I'm excited to know that there's people like you out there, Marlies, solving these tough problems. And I'm just really grateful that you're willing to give your time to come talk to us and share what you're doing.
Of course.
Yeah, absolutely. It was great to hear about your research, Marlies. I'm sorry we didn't overlap in school, but it's great to hear about your research now. And thank you for donating your time, for giving your time to tell us about your research and everything else you've told us about.
Yeah, I want to echo that thanks, and also to Darren and Andy for sharing their time with us too. My head is spinning. I simultaneously want to go unplug my Alexa and also like celebrate all of the scientists who created her. And obviously so much more. This was so great and all encompassing. I really enjoyed, and I hope everyone else did as well. Before I let everyone go, I'd be remiss if I didn't plug 2 things. The first is the opportunity to actually sort of take a class with Andy during our Alumni Day festivities on April 17th. So check out the Alumni Day website if you're interested in that. It's going to be a pretty small class, so if you are, sign up now before all of the spots are gone. And then, of course, the second thing to plug is our next Aiming High, which will be sort of a kickoff to those Alumni Day festivities on April 16th at 4:30 Pacific. It will feature our Woman of the Year and our inaugural 20Y award winner. So I hope we'll see lots of you there, but thank you to Marlies, Andy, and Darren, and to all of you for joining us this evening. This was so wonderful, and I am so grateful to all of you.
I just put the STEM website link in there for anybody who wants to see other stuff that our own robotics teams. I'm not sure, Marlies, if Mr. Whitman's sent you over there, but we have all sorts of photos of what the robotics teams have been doing since you left there. So you might want to take a look through there.
Cool.
All right. Well, this end of Zoom button is always such an awkward one, and we all disappear. So I just want to say thank you so much again, and I hope we'll all get the chance to see each other in person soon.
Thanks for having me, Megan.
Thanks, Marlies.
Thanks, Megan.
Thank you.
Bye.
Bye.